Okay, we can start today's webinar now. First of all, a warm welcome to everyone who joined. My name is Niels Verdijk and I'm one of the customer support engineers at Diabatix. I have a background in thermotechnical sciences at the KU Leuven, and I've now been a part of Diabatix for over a year now. For today's webinar, I'm joined by
Suraj Dinkar Jadhav. I'm working with Amnovis as a senior materials engineer, and I'm responsible for all the research and development activities. By background, I have done my master's and PhD in materials engineering, and I have about 10 years of experience, out of which 6 years is dedicated to additive manufacturing.
Thank you, Suraj. And during today's webinar, we'll be covering the optimized 3D printed CPU cooler with a 22% improvement. Small remark about the 22% improvement. After closer examination of the conventional design, we found out that basically our design is closer to 55% improvements, which the design itself, you can see a small sneak peek here on the right, but that's for later. During today's webinar, we'll be covering the following topics. So first we'll go over the introduction of the case study itself, so what you see here on the right. Then we'll go over how ColSim works, so how the case setup is imported into ColSim for the generative design part. Next, how that generative design is passed on to Amnovis to be 3D printed. And later on we can continue to the Q&A section, where we can go over all the questions that you had. By the way, if you have any questions throughout this webinar, feel free to leave them in the chat box. Our moderators are following this webinar and will be answering the questions during this webinar itself. Any unanswered questions will be covered by us later on in the Q&A section. Okay, and lastly, we'll explain to you where you can find both Amnovis and ColSim online and at form next. Okay, let's start with the actual webinar itself, and I'll briefly explain where the problem is, or where we are situated within the design cycle. So ColSim itself takes into account two sources of information. The first source of information is the CAD geometry and the relevant thermal boundary conditions. The second set of information is all the manufacturing boundary conditions specified by Amnovis, so the powder density, how thick the structures can be, etc. Those sources are taken into account by the generative design tool, and printable design is then sped out. Printable optimized design is then returned to you by ColdStream. That printable design is then passed on to Amnovis to be printed, and the resulting design can be seen here on the right. Let's start with Diabatix's vision. So at Diabatix, we believe that any thermal engineer can use our smart algorithms to come up with solutions that are way beyond the human imagination. So you can for sure think of a problem which reaches overheating limits, and where the human conventional designs are becoming obsolete. And that's where we come in through our product ColdStream to come up with the fully optimized design that is way beyond any human imagination, and thus very hard to find. This slide perfectly captures where we break away from the conventional design cycle. So on the left, you have the conventional design cycle, where you start from an empty design, then you could create a first CAD model, run some CFD simulations to get the thermal performance. You have to post-process those results and do some analysis of those results. And then based on those results, you recreate a CAD model to go through again this cycle until you're satisfied with a conventional design, for instance, this S-shaped design. ColdStream, as I said earlier, breaks away from this design cycle, where basically this empty design region, ColSim takes that as an input. So our AI-driven design will automatically create the intermediate results that you would do manually in the conventional design cycle, and will come up with the optimal solution. And I can show this in a short movie. in this video actually captured quite well how all these structures are added automatically, and it's fully based on the AI to determine where and how those structures should look like. That's it for ColdStream. Now I will go to Suraj's part to explain what Amnovis stands for.
Thank you, Niels. Let me start explaining with our company name, Amnovis. Amnovis word is made of two words basically. So the first one is additive manufacturing, which indicates that we are in the business of additive manufacturing field, while the second one, Novis, stands for innovation. So we would like to bring innovation or innovative products to the market with the help of our company. And currently what we do is, on one hand, we supply parts for healthcare applications, while on the other hand, our innovation stream wants to bring new technologies to the market in the form of products. We were founded by Peter Mercelis and Ruben Woutley in 2020, and we are currently based in Ascot, and we have about 10 employees. In the next slide, I would like to go over our ecosystem, which represents quite well our focus on innovation. So as you can see, we have three pillars, three fronts where we see innovation in additive manufacturing. The first one being AM applications. What does it indicate? That we want to print those applications which are not typically printed by additive manufacturing. So we would like to do that. And second, which is AM technologies. So in this on this front, we would like to use technologies which are suited for the product, and we would like to bring that technology, or we would like to start working with technology at low TRL levels, and we would like to bring it to high TRL levels and eventually to the production level. Our third front where we are working is with respect to AM materials, and a perfect example for this one is copper 3D printing, which we are covering in this presentation. And if you see all three models, all three fronts where we work in the innovation ecosystem, we choose partner quite well, and our partners are basically the ones with whom we co-develop some products. And hence when it comes to copper 3D printing, you could imagine Diabatix was such a nice partner to have. And at the end, all these innovation fronts are backed by our operational and organizational excellence, wherein we try to digitize or atomize processes so that we have elevated quality and reliability of products that we manufacture. So with this, I will suggest Niels to continue.
Thank you, Suraj. So you now had a brief introduction of what both Amnovis and Diabatix stand for, and of course, you might say that it's an ideal situation. But now we will go to a case study where we prove our facts. And we'll do that. In our case study, we'll go over the improvement of a CPU cooler. The current challenges with CPUs is, as you all know, Moore's law, that the amount of transistors per unit of area is increased or doubling every 2 years. And that will, as a consequence, put a higher heat input per unit of contact area. And because of this, conventional designs like skived heat sinks are becoming increasingly outdated, which require us to move to custom designing to facilitate those new cooling challenges and of course manufacturing issues. Skived heat sinks have the following limitations. First of all, as you might imagine, the orientation of the fins is fixed. Once you start skiving those different fins, the orientation is fixed. You can't skive as well any distributor. So once the flow enters in between the fins, it can't be redirected inside of the bounding box of those fins. And you need a silicon part like this one. This will sit between the skived fins at the bottom and the inlet at the top. Yes. And this is made out of silicon because it's easy to make. And of course, it has no impact on cooling. Quite the opposite. It acts as a bit of a thermal insulator. Those are the issues with the conventional, cheap manufacturing techniques.
Yeah. So, considering the limitations as suggested by Niels of skiving manufacturing process and the potential of additive manufacturing to create complex shaped, near net shaped parts, we at Amnovis decided to have two objectives for copper printing, and the first one was to produce crack free and fully dense part, and preferably using the conventionally available machines which are enabled with laser power output up to 400 watts. And the second objective that we had in mind, that the manufactured part should have a better combination or the best combination of strength and electrical or thermal conductivity. But perhaps electrical and thermal conductivity both go hand in hand. Okay, so typically people say that when it comes to thermal management applications, it's the only thermal conductivity or electrical conductivity that matters. However, I would like to bring your attention to one more important point, that as you go to complex shapes and thinner dimensions, it is important to note that the thin wall thicknesses should also sustain the pressure of the fluid that is inside. That's where the conductivity comes into picture. And if you look at material index for heat exchangers as per the Ashby's methodology, then you would see along with thermal conductivity there is another component which is yield strength that is there in the equation. So which means in the end you need both electrical conductivity, thermal conductivity and the strength. So with that I will give floor to Niels.
Thank you, Suraj. So this was a very brief introduction about what we will show now with the case setup, and then we'll now go over all of those different steps individually, starting with the optimization part on ColdStream. So ColSim itself is not a CAD tool, it's basically an optimization tool where you fill in all the boundary conditions and get a resulting design. And on ColStream you will have 5 steps. First, you need to upload a geometry. So in the pre-processing step, you create your CAD geometry, which you will already have if you would go to using the conventional design. So that CAD geometry you upload then to ColdStream. You fill in all the relevant boundary conditions. So what regions are all solid, what regions are all fluid. You fill in the missing boundary conditions, so the inlet temperature, inlet velocity, outlet condition, heat input. Then you finally complete with setting on the targets and specifying the design region. And after that you can end with the CAD file itself. I'll now show it on ColSim itself. Well, go to yes. So this is ColSim. Here I can see this is the CAD model that I prepared for this particular webinar. So where we did the actual optimization with. On the left, you see the regions tree. So those are all the entities that I uploaded to ColStream, where we have a copper cold plate. So this is the base of the copper heatsink. We have a coolant geometry. So this defines where the fluid, the coolant, can flow inside of the domain, with both an inlet patch here on the top and an outlet patch here at the end. And finally, a housing geometry which contains everything. So basically, you go upload all the entities to ColdStream and you fill in the relevant information. So for the copper cold plate, we define it, of course, as a type solid. We gave it the copper cold plate name, and we defined it to be made out of copper. Next, we have our CPU itself, which we modeled as a boundary patch, a surface patch in our CAD model. We defined it to be of type heated wall, and we specified a volumetric heat flow, heat flux that comes in through that entire surface area. And for the optimization itself, we want to minimize the temperature, of course, so we impose a temperature minimization objective. Next, we have our coolant. I'll quickly hide this because it's not needed anymore. I'll quickly hide this as well. So this is our coolant itself, which is of course of type fluid. And the coolant we'll be using is a water glycol mixture with a 4060 volumetric weight. fraction. And we'll use the default K omega SST model as it's very appropriate for this particular case. As an inlet condition, we specify a fixed flow rate inlet. So basically, where we impose a fixed flow rate inlet, no matter the pressure drop. And we specify incoming volumetric flow rate of 0.82 liters per minute, rounded off to cubic meters per second. This will be this value. And we specify an inlet temperature of 40 degrees Celsius. And we limit the pressure loss to remain below 140 kilopascal, which is a very high number, just to be sure that the trivial solution will not be returned. And at the outlet, we'll just specify a pressure outlet condition, just letting platform know, okay, the flow is just going to some bulk outlet storage. Next, we define a subregion. This subregion will let the platform know where to add the structures, so that those are the structures that will be printed by Amnovis. So it's of type design. And we specify 3D printing with an RF min, so the minimal size of the structures of 0.28 millimeters. So that's very, very tiny. And of course, those structures are made out of copper. And lastly, we have our housing geometry, which is just a solid made out of some plastic. Okay, so that's the input to ColdStream. Once everything is filled in, the platform, the optimizer takes over and will do all those iterations which you saw in the video which I showed you earlier. And then you'll get to an optimized design, which looks like, if I can show it, yes, hide others. This is the design that is optimized, that will be returned by ColSim to you. Or perhaps I will show it with the fluid region, which makes a bit more sense, because then you can see all the channels that are being formed. And I'll color it by pressure drop. Yes. So if we look at the fluid region, we can see that of course the incoming fluid is going down, moves into this distributor part, and is then redirected all over all those little channels to cool down the CPU, which, as you will remember, sits right here below it. So this is the cooling channel, the cooling effectively. All those little channels will end up in a nice collector, which will then redirect the flow towards this single outlet point through which it leaves. Okay, let's compare that to a conventional design. So ColSim allows you to do both simulations and optimizations, and allows you also to compare the two. On the left, we have the performance values of the optimized design, where we are of course interested in the heat source itself, and compare that to the conventional skived heatsink on the right. So we can see with the optimized design, we see a maximum temperature of the CPU of just over 56 degrees Celsius. Compare that to the conventional skived design, where we see a maximum temperature of just over 76 degrees Celsius. So it's a 20 degree improvement on a 20 degree, or slightly over, or slightly under, 20 degree heats up. That's a massive improvement because of the additional complexity that comes with 3D printing. Okay, and of course, once the optimization has finished, you can press the download design button to get the CAD file with the optimized design, which you can then send over to your to your 3D printing partner, Amnovis preferably. Sorry for the plug. And now Suraj will take over again to explain the 3D printing process.
Yeah. So thank you, Nils. So in coming 2-3 slides, I'll explain about copper 3D printing that we use at Amnovis, and I will also dig a bit deep into what this technology is and why we think we have better processing at copper printing at Amnovis. So to start with, for those who don't know, I'll still give some background about 3D printing. So 3D printing is nothing but also called as additive manufacturing, and it's a family of manufacturing processes, and in which laser powder bed fusion is a process which uses laser as a heat source typically what we do is we get a CAD file, we orient the part as we want to manufacture, and then we cut it into different slices, and this slice thickness is predetermined. And once once we have part in a sliced manner, we give this input to the machine, and the rest process is shown in this video, as you can see. Give me a minute, it's not working. Yeah. So so what happens, based on the CAD design, a layer of powder is spread on the base plate, and then a laser with known power and scanning speed is allowed to interact with the powder bed. With this, the powder is melted and attached to the base. The process of layer deposition and laser irradiation is repeated until you manufacture the final component, as shown in this video. So as you can imagine that in this case, maybe I will put a laser pointer so that it's, yeah. So as you can see, in this case it is important that there is a good laser metal interaction, meaning the energy that is there in the laser should be transferred to the powder in order to melt it and form a stable molten melt pool and to manufacture component. And but what happens typically is, for all laser absorptive materials like titanium, iron or stainless steel, for them the processability is very stable, which is typically indicated by such a graph, which is on y-axis you plot relative density of the part, and on the x-axis it's volumetric energy density. So volumetric energy density is nothing but a ratio of laser power divided by scan speed multiplied by hatch spacing and layer thickness that we employ. So there are three characteristics that are important in this graph to have a stable process. One thing what you want to have is, you want to have 100% dense part, which is here. And next thing what you want to have is, ideally, preferably, it should be, the graph should be on the left side, meaning you consume less energy. And the third thing that you want is this the plateau that is shown here, the flat one, should be as long or as broad as possible, because when you typically use powders in laser powder bed fusion process, they get aged over time, and their optical absorptivity might change over the period of time. And that's where, without you changing the process, the processing window might alter here and there. So the process parameter that gives you fully dense part now may not give you fully dense part 1 year later or 6 months later. That's why it's crucial to have this window as broad as possible. And we typically call a window, let's say on the left side we call it conduction controlled melt pool, where if the energy is not sufficient, we have lack of fusion porosity, and as you can see, it is reflected into decrease in relative density. While on the right side, it's a keyhole mode melting we call. And if you go still further with the power, again the part density decreases, because you have keyhole induced pores, and we don't want both of them. What we want is, we want to print a fully dense part and in a broader processing window. So what happens typically for copper, why it's challenging, is because in case of conventionally processable alloys, you can see there is a broad processing window, but for copper it's a very narrow processing window. So you need to be, if you want to get fully dense part using infrared laser, you need to be in the keyhole regime, and that too, what you can see is if you move away from the optimized setting by a bit, the part density is drastically goes down, be it on lower power side or be it on a higher power side. And this is due to the high thermal conductivity that plays role by dissipating a lot of energy. So in the next slide, and one important point I failed to mention is, you can see that the processing window is quite narrow, which means it will have its own challenges about process stability. In the in the next slide, I will tell you why the causes behind the small processing window. And the first and foremost cause is copper typically has high laser reflectivity at the infrared laser wavelength. So in laser powder bed fusion, in most of the commercial machines, a solid state laser with a wavelength of around 1070 nanometer is used, and as you can see, the absorptivity or absorption coefficient of copper at this wavelength is very low. So which means that the laser energy will be reflected nearly up to more than 95%. So the energy cannot be absorbed. That's where you cannot melt the copper powder and you cannot produce a part out of it. However, as you can see, when you go towards shorter wavelength, meaning in the visible region, the optical absorptivity of copper drastically goes up. And that's where one of the ideas come that I will discuss in the solution section. The next challenge that is there, which affects the small narrow processing window, is high thermal conductivity of copper, and we actually want thermal conductivity, so we have to make sure that this parameter doesn't get affected when we process copper parts. And third and the last is solidification thermal driven cracking. And in my experience, what has happened is this is typically due to some impurities that are there in the raw material, because the raw material used to design for conventional manufacturing, whereas for additive manufacturing those impurities cannot be removed during processing and they stay inside and they create cracking. So that's what I saw it, but with recent knowledge in this segment, this problem also has been eliminated quite a bit. So as you can see, as I have explained all the causes, on the right side I give potential solutions. So the first and foremost solution that people are using is the use of green or blue lasers. And as I explained in this graph, that why someone would use green and blue laser is just simply because you want to improve the optical absorptivity, and that's the case. People are now manufacturing copper components with green and blue laser, but there are two things that needs to be addressed. Thing number one is green and blue laser, the quality of those lasers is not yet there compared to infrared lasers, which is typically measured by so-called M² factor, and that is one case. And second case is the cost of these lasers is still high. There are these two challenges which are still to be tackled for the visible lasers. The second approach that typically is being opted is use of high power infrared laser. So what it indicates is that you use the same solid state 1070 nanometer laser, but you increase the power in such a way that you increase the absolute energy transfer to the to copper powder. What happens is, because of that increase in absolute energy transfer, copper powder melts, but you could only print and copper powder melts and you create a keyhole. And this idea is based on using the keyhole feature of the melt pool. And when you have a keyhole, it's basically a hole inside a melt pool. The laser goes inside and gets trapped within that hole, and it can have multiple internal reflections and it has no way to escape than absorption. That's where your optical absorptivity increases in this approach, and you could be able to manufacture a dense part. However, there are two major challenges. One, because of this reflectivity, it might damage the optical system of the machine and also some hardware components. The second is the keyhole itself is not stable. So keyhole mode itself is not stable, so it also has its own challenges. To further strengthen this approach, there can be few more solutions can be implemented, such as you can use low thermal conductivity base plate, or you can use preheating of the base plate before you start the machine. And another approach is playing with powder particle size distribution and powder pre-alloying, but they will assist they will work best in combination with high power laser solution. And the last approach is related to powder surface modification. So the idea here is that you coat copper powder with a very thin layer of alloying elements in a way that the thin layer absorbs the laser light, and that's where the laser energy is converted into heat, and the rest, copper likes heat, so copper would just absorb and melt and form a part. So in the next slide, I have done categorization of these potential solutions, the first being green and blue laser. The basic idea here is copper absorbs visible light, so that's how your absorption is increased. The next is there are some approaches which are coupled with infrared laser. Here we are using basically keyhole mode melting in order to fabricate the part, while the third one that was related to powder surface modification, and here the idea was that we increase the optical absorption but we don't change the laser itself. So what we do to tackle the copper 3D printing issue is we are using the latter two approaches, so category the second and the third that we mention here. And by using by using these two approaches, what we are able to do is, as you can see in the schematic here, we could able to broaden the processing window from this size to that side. So please note that this is just a schematic representation, but in simple language, to get the same density, we could probably do 3 times or 4 times faster, which also makes us more economical as compared to our competitors. In addition to that, as you would see in from our properties, that our combination of electrical conductivity and mechanical strength is quite attractive or lucrative for our customers compared to others. So because of our process stability, we were able to manufacture such a complex shape part, thankfully designed by Diabatix. And as Niels mentioned in his slides, that with skiving there are some technical issues or manufacturing issues that are there, where there is also a limitation with respect to orientation, whereas in case of Diabatix, because it's a generative design, you can see the channels are oriented in all possible directions, and in addition to that, the minimum feature size in this part was 280 micron, and as you could see in the figure, we were able to successfully print it. So it explains that the competency of Diabatix in manufacturing or creating those complex shape designs with improved performance, and our manufacturing ability is up to the mark to manufacture those parts. In the next slides, I would like to give you overview of mechanical, electrical and thermal properties that we achieve at Amnovis, and I would like to mention one more point, that whatever we present here, that was IP protected, thankfully, and because of that IP, we are the only one who could process with those approaches. So this table gives you overview of mechanical, electrical and thermal properties that we achieve for a copper chromium zirconium alloy as a case alloy. So if you look at the thermal, and again I have given comparison of similar properties from 3 different companies. So if you look at electrical conductivity, you could see that mostly we are more or less equal to the electrical conductivities of other companies, whereas if you look at our mechanical strengths, which is like around 500, yield strength is around 500 megapascal, up to which we can reach, and the tensile strength is around 600 megapascal. That is quite high in our opinion. And as I explained in the first slide, that combination of yield strength and thermal conductivity is important when you design the heat exchangers, and not only electrical conductivity when it comes to some complex shaped parts with fine features. in addition to that, despite having those high mechanical properties, we also get elongation quite high. In some cases, it's beyond 20% and with 500 megapascal in strength. So with this, I would like to hand over to Niels.
Thank you, Suraj, for that very excellent explanation about 3D printing. What we covered up until this point is very theoretical. We of course showed you, like in this piece, that we could print, or that Amnovis could print the design generated by ColdStream. But the experiment, or the validation, or the check between the conventional SCIF design that you see here on the right and the optimized 3D printed design on the left, it's quite theoretical because it's all a numerical optimization. But we are currently in the works with KU Leuven to do some experiments to do both, to validate both, basically performance of the conventional design and compare it to the 3D printed optimized design. So that's in the works, and that should be ready in a potential future webinar, or for sure at Semiterm, where both Amnovis and Diabatix will present. Okay, that leads us to the end of the webinar, and I would like to wrap up everything both on Diabatix side and on Amnovis side. So very briefly, the main benefits of using ColdStream is the design cycle is reduced dramatically. Our designs take up 1 to 3 weeks, compare that to classical engineering, where it takes a couple of months. So that's a huge improvement in speed up of the design cycle, and it's also purely AI driven, so no manual engineering time is taken into account as well. If you would like to build your own ColdStream, you would also need, of course, a supercomputer, which we provide for you as well. For Amnovis' part.
Yeah. So in this slide, I have summarized what are the benefits of working with Amnovis. Thing number one, we have proprietary powder and processes which are patent protected, wherein we use optically absorptive powders. So you could imagine that we are able to, that's where we are able to print copper components with conventional machines equipped with fiber lasers. On top of that, the powder that we have is robust against oxidation, and it has excellent flowability and packing density, which are these properties are crucial for laser powder bed fusion as such. The second category is because we have a broader processing window. As you could imagine, or even if we print today or after 6 months or even after 1 month with the same powder, you can expect reproducible and trustworthy results for your parts. And because we use lower powers relative to others, so it gives us opportunity to go down to up to 200 micron thickness feature size, and that can also be tuned up to the application that is necessary. And the last but not the least is related to part properties. So as I mentioned, the components that we manufacture, because they are produced at a faster scan speed, there is something called solid solution or supersaturated solid solution that can be achieved better, perhaps in our case compared to the others, because when you scan slowly, it's possible that you allow some more time to cool the part, and that's where supersaturation may not be as equal as us, and that's where it gives us an opportunity to increase the strength even higher by applying a suitable post heat treatment. So in nutshell, our properties are tolerable, and we could go up to 90 ISCS or around 360 watt per meter Kelvin when it comes to thermal conductivity. And we not only have additive manufacturing or setup in our company, but we also have a post-processing setup in-house, which makes us attractive, because then we could do all things together, and you will get parts as soon as possible. And with this, again, I would like to hand over to Niels.
Thank you, Suraj. Looking at time, we're way over the 30 minutes, so we'll skip any questions for now. Do know any unanswered questions will be answered later on via email. And of course, let's end with where you can find us. So if you want to try ColSim for yourself, feel free to take a screenshot, of course. You can simply insert this into your URL, and you'll be able to grant it access to the ColSim viewer account, where you can have a look at other finished demo cases. Or if you want to know more and want to contact the team, feel free to email at info@diabatix.com, or feel free to reach out to this number. Same for Amnovis. You can find their website here, www.amnovis.com/copperlpbf, or contact Amnovis at info@amnovis.com, or of course feel free to reach out to this number, and of course feel free to take a screenshot as well. You can also find us at ForumNext within a few weeks, next week, sorry. So Diabatix can be found in Hall 11.11 booth A61, and Amnovis can be found in Hall 12.1 at booth D21. Thank you very much for your time, and hope to see you at ForumNext.
Thank you.
Bye-bye.
Bye.